Hi, I'm Rich Fulcher, a designer and manager on the Android design team here at Google. At this year's Google I/O conference, we introduced material design, a new visual language for creating bold, graphic interfaces driven by typography, scale, color, and position. For me, one of the most exciting things about material design is how it takes these classic principles of print design and brings them to life. The materials take energy from the user, from their finger, from their mouse click, their touch, and they take that energy and use it to transform and to animate. Today, I'm going to talk about how these virtual materials of paper and ink pack much more power than their real-world meat space counterparts. Now, every pixel drawn by an app is a dot of ink on a piece of paper. Paper has no color, but ink can be any color. And ink coloring is how all content is displayed, whether that's the controls of your app, an image, or even a video that's playing. Paper can be a variety of widths, the x-axis, and heights, the y-axis. It can even fill the entire display such that you can't see the edges of that paper. Or it could shrink down and just be the size of a single button, no larger than a 48 by 48 dip square touch target or standard target sizes. Ink doesn't have any of those restrictions. It can be any size, so long as it fits within that paper. You've got to have something to actually apply that ink to so that it can be seen. Paper has an absolute fixed thickness of 1 dip. That's equivalent to a 35-pound weight piece of paper, so kind of a light cardstock. Now, when you add ink, you're not changing that thickness. This isn't kind of paint that's building up layer and layer and layer and making it thicker and thicker. The paper itself is always that 1 dip thick. It's never 0. That would be a hologram. And this isn't hollow. This is material. That sense of tactility is vitally important to the system. In terms of shapes, paper wants to be a rounded rectangle, whether that's a rectangle or a square or even a circle, which is just a really, really, really rounded rectangle. It doesn't want to be a triangle. It doesn't want to be a concave shape like a star or the shape of your app icon. Now, ink doesn't have these restrictions. It can be any shape, and it can cover all of those things you want it to be. Those are the basic principles, but how do all of these materials live and move within a more complex structure? Well, we need to start by talking about depth, and that means embracing the z-axis. Now, every device has a physical z depth. For a handheld device, it's that distance between the glass on the front and the back of the device that rests on the palm of your hand. Now, that depth controls how paper can behave. So paper wants to respect that device's depth. It doesn't want to be able to flip over, because if it were to do a move like that, well, that paper is going to start to move and it's going to bonk against that glass on the front of the device or against the metal on the back. It can't execute that move and maintain that sense for the user that it's inside that device, just between those front and back slots. That's why we don't do paper flips. When we have paper, it casts a shadow, and that shadow is based on its position within Z. Now, paper is generally presented as square to the user. Just like I'm moving my hand back and forth in front of the camera here, paper moves to the user's eye in the same fashion. Now, paper will cast a shadow when 2 pieces of paper slightly overlap like that. The one in front has a light source in front of it. The paper behind it isn't getting all of that, so it's getting a shadow on the back. We like to keep the paper square. We like to make sure that the shadow isn't something that's being drawn as ink, that's being printed on the paper. It comes about because of the physical relationship, because of the lighting model that the system gives you. When we have paper, it's solid. When the user reaches out and touches it, the user can never press through the paper. It just kind of makes contact and it's there. Now, we do respond to the user in a couple of ways, though. One is that as the user approaches the paper and they make that touch, the paper will rise to kind of meet them. So there's this illusion of the glass here. Your finger comes down on the glass. The paper completes that motion by coming forward to meet the user's finger. You might think about it as, imagine your finger kind of pointing down on a reflecting surface of water. And as you get closer and closer, it sees its reflection, and those two touch together. The way that ink responds is like the ripples that would happen on the water. As I hit that surface, I break the surface tension of the water. I get this pleasant circular rippling that occurs out of it. That's what we do in the ink to kind of communicate that not just that you've made contact with the paper, but which of the particular elements, ink elements on the paper you've touched. Now, motion is all about establishing and emphasizing the continuity of important elements. And the paper can move across any of those three axes. It can move along X, it can move along Y, even along the Z. Now, material can do more than move. Part of the magic of the experience comes from a way that materials can change, the ways that they're not bound by these boring physical laws of the known universe. So paper can change its size in both the X and Y position, and ink can do its own thing. It doesn't have to do exactly what the paper is doing. So you can do things like have a piece of paper resize and have the ink remain at its same size, but just reflow to take advantage of that new spacious real estate. Or you could expand and have the ink expand at the same rate, or you could leave the paper at a fixed size and have the ink just grow or shrink within that. They're completely independent. Now you can change the width and the height of paper differently. They don't have to be symmetric, they can be asymmetric. And that's really important for when we do transformations. We strongly encourage this. So in the example over here that you're seeing tall objects being made to feel taller. You're seeing wide objects made more broad. Now, why is this asymmetry important? Well, it helps the user understand the difference between something that's resizing and staying in that place and something that's moving within Z. If I move within Z, that's kind of the same as a symmetric scale. As it gets closer, it's growing in both aspects at the same rate. By doing resizes asymmetrically, we're letting the user know, okay, that content is actually staying at that same Z level. The movement is a different signal to them. Now, paper can change between its shapes, but it does like to kind of start at and return to those core shapes we talked about before, those rounded rectangles. And like some kind of X mutant paper, paper can split, snicked, or it can join. Those materials can heal together, they can regenerate, they can kind of connect back up. Creating or destroying paper is always associated with motion. Now, paper can enter and exit in different ways. Those can be independent. There's three main styles. You could just kind of create paper in place and destroy it in place. You can have it enter one way and exit a different way. Or you can actually have paper kind of clone. So there's one piece of paper, it clones and creates a second one, which can then move, and then it can rest back down and heal and just become one piece of paper again. So how do multiple pieces of paper interact with each other? There's two key types of arrangements. The first are seams, which are created when two pieces of paper share the full width of an edge. It's like they're stitched together at a common side. Now, when paper meets at a seam and joins in that way, it moves together. They're actually connected, so they'll move as one. The other is a step, when we have two pieces of paper with different Z positions that overlap, and you get that shadow we talked about, then you've created a step. These two papers don't have a relationship to each other, so they can move independently, one of the other. A very common way that we'll see a step is for a toolbar, where you have a step above a larger, usually a larger sheet of paper that can slide under it. Now, there are variants to this. You might start with the toolbar and the other piece of paper seamed together, and have the toolbar just rise within Z just as it needs to accommodate the motion underneath it. So it could lift to make room. Or you can reverse that. It could move backwards in Z, and the other piece of paper could come up and cover it. Or finally, you could just kind of leave them seamed together. The other piece of paper pushes the toolbar up, and it just pops off, and then you only see the other piece of paper present. When paper passes over a toolbar, it's important that you not split any of the actions the toolbar might contain with the piece of paper. You want to make sure that the actions are on one side or the other. And one last note about toolbars, just like any piece of paper, they can resize. So they can start tall, and as the user scrolls, they can shrink up, or you can reverse that motion as they move the other way. The one thing you'll want to keep in mind is that it's best to have the toolbars snap between those two positions instead of just getting stuck in that middle ground between them. You want to kind of crisply move to the smaller or the larger sizes. Another signature element in paper is the floating action button. We nickname it the fab. A fab can straddle a seam if it relates to the content of both of the pieces of paper that are meeting at that seam. Or it can straddle a step if it relates to the piece of paper that's creating the step, the one that's more forward in Z. Now, you don't have to put a fab at a straddle point like that. It doesn't have to be on a seam or a step. It could just be on a piece of paper, conveniently tucked away in a corner, or really anywhere within that paper surface. And you want to avoid doing things like artificially creating a seam or a step just to give your fab a place to live. Those seam and step relationships should be about the structure and the interrelationship of those pieces of material, not about just having a decorative point. If you want to learn more, our guidelines are a great place to start. If you go to www.google.com/design or specifically /spec, you can read about all of our material design guidelines, and you'll see a bunch of examples that can help you get started with this. There are also a ton of resources there waiting for you to download them. Sticker sheets, templates, icons, even fonts are available for you from that site. Thanks for watching, and I hope you have a lot of fun designing with material.